Hello, everybody, and thank you for joining us today. My name's Adam Wierman, and I'm a professor of computing and mathematical sciences and the director of the Information Science and Technology Institute at Caltech. It's my pleasure to welcome you to this special event featuring a recent recipient of the Caltech Distinguished Alumni Award, which is the highest honor that Caltech bestows upon a graduate. Today's an opportunity to celebrate and learn from Dan O'Dowd, who is the CEO of Green Hills Software. I've known Dan for quite a few years now, and you're in for a treat. He's always provocative and stimulating, and today just might change the way you look at software in the world around you. Following Dan's presentation, I'll be moderating what I expect will be a lively Q&A. So I encourage you to submit your questions into the Q&A feature at the bottom of your screen, and we'll get through as many as we can. Now, it's my pleasure to invite Thomas Rosenbaum, Caltech's president, to join us and formally introduce Dan. Tom?
Thank you, Adam. It's a great pleasure to welcome you all to this very special event. As Adam noted, Caltech's Distinguished Alumni Award is the highest honor the Institute bestows upon a graduate. It was initiated in 1966 to recognize the outstanding achievements of our alumni, whose leadership in fundamental discovery and technical innovation exemplifies the essence of their Caltech training. The Institute's contributions to society emanate in large part from the accomplishments of our graduates. And today we celebrate the work and vision of a 2020 DAA recipient, Daniel O'Dowd, the founder, president, and CEO of Green Hills Software. Dan earned a bachelor's degree in engineering and applied science from Caltech in 1976. Where he began studying mathematics and then focused on computer science in Caltech's newly minted CS option. Dan began his career at APH Technological Consulting, followed by National Semiconductor, where he worked on architectures and embedded development tools for microprocessors. In the late 1970s, Dan also designed a microprocessor for JPL that was used in the Mars Orbiter camera on board the Mars Global Surveyor. The MOC operated Mars orbit from 1997 to 2006, returning more than 240,000 images of the planet's surface, images that were used to create a high-resolution topographical map of Mars. These images helped determine drive routes for the rover Opportunity, which operated on the Red Planet from 2004 until 2018. This is 40 years after Dan's original contribution, a long-lasting contribution for sure. In 1982, Dan founded Green Hills Software with his colleague Carl Rosenberg, serving as the company's president and CEO. Ever since, he has pursued his passion to fix bugs in computer code, a passion that he developed as a student at Caltech. Over nearly 4 decades, he has built his company into the worldwide leader in embedded safety and security, creating certified safe and secure real-time operating systems and development solutions that support a broad range of hardware and software platforms used in multiple industries. These include commercial and military avionics, self-driving cars, and remotely controlled medical equipment. Dan urges the technology industry to prioritize security by regulating and safeguarding software and products that could endanger human lives if they were to be compromised or malfunction. As a leader in the industry, he recognizes that individual effort is not enough. Widespread coordination is required. And here I quote from Dan: "I work on technology, but I also have to get people to understand the fundamental ethical problem so that the decision makers will make the right decisions. When I was a student at Caltech, there was a course on engineering ethics, which taught us that we could design a product that wasn't very good or of low quality, but that we must say no at the point when we realize a device is an outright danger to humanity. To refuse to make a bad product is an acceptable moral choice, but a potentially insufficient one. At some point, you have to call it out, become the whistleblower, and foster support from other people if you believe there's a tragedy or catastrophe in process." Today, we honor Daniel O'Dowd for his entrepreneurial leadership, transformative technical contributions, and dedication to the highest ethical standards in service of society. We are also grateful that Dan loaned us his son, Richard, for 4 years to receive his own BS in computer science at Caltech in 2013. Dan, over to you.
Hello, everyone. And thank you, President Rosenbaum, for that wonderful introduction. I'm truly honored to be a recipient of Caltech's Distinguished Alumni Award. My affiliation with Caltech has always been important to me. Today, I would like to talk about how we can make computers safe for humanity. I started studying the process of software development in 1975 when I was a student at Caltech. I recently found a large sealed envelope that was labeled Bug Reports, August to September 1976. It contained a description of each of the 200 bugs that I fixed over a 30-day period. I don't remember making this time capsule, but I do have a policy of keeping souvenirs from each project I work on so that I will remember what I did with my life. Each bug report stated the nature of the bug, how it manifested itself, how I found the underlying error, how long it took to find it, how long it took to fix it, what I did wrong. I also noted what I could do differently that might avoid making similar mistakes in the future, or if I made them, find those mistakes and fix them more quickly. For the last 46 years, I've dedicated my life to studying software development. And I have some good news, and I have some bad news. First, the bad news. Computers have become a grave threat to humanity since we started hooking them up with every safety critical device to the internet. The software was never intended to be used in systems that people's lives depend on. When the worst consequences that could result from a bug in software is that you might need to reboot your computer or lose some of your data, the move fast and break things policy that is prevalent at every tech company today is the road to immense riches. But now that immense body of software and the move fast and break things methodology dominates the software in our cars, the electric power grid, water treatment plants, chemical factories, and voting machines. The consequences of a single error in all of that software can now be exploited to easily disable, destroy, or commandeer and turn against us everything our lives depend on. That software is riddled with bugs and security defects that can easily be purchased from hackers, enabling any tin pot dictator or billionaire to destroy all of our critical infrastructure, like the electric power grid, leaving us shivering and starving in the dark. The survival of modern civilization and the 8 billion people whose lives depend on it now requires that the software that runs the world never fails and can't be hacked. Unfortunately, the software that now runs the world is deeply defective. We've been living in the first age of software development. It's like the dark, it's pitch dark. Software stumbles forward, frequently tripping and falling on its face. Software reliability and security is a nightmare. We fear the wild animals of the night, the hackers and criminals and spies that steal our money, our privacy, our personal information, and our technology. And now they can kill us all with the click of a mouse. But this talk is not about how bad it is, or how much worse it will get, or even our ultimate doom and destruction. I don't have to give those speeches anymore because it's all been thoroughly documented in 2 recent books. This is How They Tell Me the World Ends by Nicole Perlroth, and Click Here to Kill Everybody by Bruce Schneier. These are both extremely well-researched books that show the ease with which our systems are being hacked and how they do it and how often they do it and why they do it. You need to read these books, and you need to get your friends to read them too. Only then will you understand our precarious position. So that's the end of the bad news. Now for some good news. 25 years ago, I developed a new methodology and technology to support it that enables the development of software that never fails and can't be hacked. Since then, I've designed the core of the software security system for hundreds of the world's most critical software systems, and none of them has failed or been hacked. When software development makes it into the light of day, software will be able to see the pitfalls and avoid tripping and falling on its face. We will be able to see the wild animals coming at us and dispatch them before they can reach us. We can ensure that all of the software that our lives and the quality of our lives depends on never fails and can't be hacked. This new methodology for software development will bring software from the night into the day. That's why it's called the Dawn Project. I developed the Dawn methodology to deliver on the contract I won with Boeing to develop the operating system for the B-1B intercontinental nuclear bomber in 1997. The operating system controls everything in the plane: flight controls, navigation, communications, and weapon systems. After years of studying why operating systems had so many bugs and security defects, I designed a new operating system from the ground up. Its only design requirement is that it be secure. No trade-off is ever made between features and security. Until a feature can be proven reliable, safe, and secure, cannot be incorporated into the operating system. The operating system is minimalist. It does nothing other than what it must absolutely do. It is simple, sparse, and orthogonal. But it is capable of doing everything that other operating systems can do. And it can run on any computer system. I wrote it in my library, delivered it to Boeing, and supported it until it was flying. More than 20 years later, it's still flying in the B-1B. It's also in the B-2 stealth bomber, the B-52 bomber. It also runs everything in the latest F-35 and F-22 fighter jets. It's also in the F-16 fighter jet and the Boeing 787 and Airbus A380 commercial airliners. The Dawn methodology has been used to secure, or will soon secure, all of our nuclear forces, all of our military aircraft, most recent commercial aircraft, and our top secret encryption devices and communications equipment. Recently, I've used the Dawn methodology to build a secure laptop for all FBI field agents and the only secure cell phone for the military, and every General Motors car for model year 2020 to 2023. We have made a good start to making safety and security critical things never fail and never be hacked. There is now light in the software world, but it is not the day, it is only the dawn. Nearly all of the cars, the electric power grid, oil and gas pipelines, water treatment plants, and voting machines are running software that fails frequently and is easy to hack. Most of the companies building this equipment are unwilling to invest what it would take to do their software right. That puts us all at risk. They prefer to roll the dice, hoping against hope they won't be hacked and their customers won't be harmed. This is not where we need to be. The software base that we rely on was not designed for safety or security critical systems, in which one tiny error can lead to countless fatalities. The iron law of security says that security must be designed in from the start. An insecure system can never be made secure, no matter how much time and money you throw at it. And this software was designed wrong from the start. The current software that runs the world can never be made secure. But the software that runs the world must be secure. That's quite a dilemma. But as Sherlock Holmes said, once you eliminate the impossible, whatever remains, no matter how improbable, must be the truth. To survive, we must rewrite the entire software base that runs the world from scratch, using methodologies that will enable this software to never fail and never be hacked. When this is done, we can build the world the dreamers describe, where technology is our friend and ally, not our master and the means of our destruction. Most people think I'm hopelessly naive for thinking that we could replace the code bases which trillion-dollar companies defend. But their might is built upon a foundation of quicksand, consisting of millions of critical bugs and security defects. I agree. I probably can't convince them to change. They are unlikely to look favorably on someone who says their software needs to be rewritten and they are a threat to humanity. But who knows? Maybe I'm just a curmudgeonly old pessimist, and after everybody sees this speech, they'll appoint me world security czar. They'll divert $1 trillion from the new infrastructure package to my program. And in 6 months, we'll have everything important secured, at least temporarily. And in 3 years, we can redo the whole thing and everybody's safe and everybody's happy. Maybe everybody will embrace this obvious inevitability of this new dawn methodology. We can all hold hands and sing Kumbaya on the way to the future. Just in case that doesn't happen, I do have another plan. Whenever a disruptive technology emerges, few, if any, of the old leaders survive the transition. It happened to the vacuum tube manufacturers after the invention of the transistor. Embracing the new 32-bit microprocessors introduced in 1979 enabled a few 24-year-olds like Bill Gates, Steve Jobs, and me to displace the dominant software companies in a few years. And again, when Steve Jobs introduced the smartphone, he wiped the dumb phones off the map in a few years. Again and again and again, every purveyor of the old technology, no matter their wealth, power, market share, or monopolistic lock-ins, they're all swept away in the tidal wave of new technology. Of course, for everyone to be swept away in the tidal wave, the new technology must actually deliver, not just promise, something that is far better than the entrenched competitors. So, is the value of never failing and never being hacked a sufficiently large improvement to a product to enable a small company to win an exponentially growing market share from much larger entrenched competitors? Imagine you were a salesperson for a startup electric vehicle company, and its electric vehicles work perfectly all the time, and no one could ever hack into them. And every potential customer knew that it was easy for hackers to commandeer your competitors' cars and crash them into oncoming traffic anytime they felt like it. I could make that sale at a 20% higher price. Most people value their family's safety more than to put their kids in a deathmobile in order to save 20%. Do you think you could sell millions of cell phones that can't be hacked for more than the price of an iPhone? We will soon know. I have one. I use it for my confidential calls. A cell phone developed completely from scratch, from the ground up. We wrote all the code. We wrote it right, and it's an unhackable cell phone. Will people pay more money for that? We'll find out soon. It's going in the market in a few months, unless the government jumps in and buys them all first. In a few years, any company using the DAWN methodology can build a product that never fails and can't be hacked. They will be able to sell it against any entrenched competitor for significantly more money. Rapid exponential growth of sales at higher prices than competitors, such as you see with Tesla and Apple, generates a high value in the stock market, giving the company easy access to massive amounts of new capital. And it makes takeover attempts by an entrenched competitor to shut down the new technology prohibitively expensive. Even though Tesla's market share is only about 1%, it's worth more, far more, than any other entrenched car manufacturer. An entrenched competitor will usually ignore a new market entrant until their market share reaches 5 to 10%. As the new company keeps growing exponentially each year, the entrenched competitors will finally conclude that they need software that never fails and can't be hacked just to compete. But they will probably try to secure their obsolete product rather than build a new one based on a secure and reliable foundation. Of course, the iron law of security tells us they can't do that, so their products will continue to be riddled with bugs and security defects. The new competitor will continue to claw market share out of the formerly entrenched competitors who are now struggling for relevance. In 5 to 10 years, the new company will overtake the entrenched competitors, which spells their dooms. The impossible has been achieved. We've rewritten the entire software base for an industry in a secure and reliable manner. We have extended the domain of software that never fails and can't be hacked to include a new industry. Now, people ask me, what is this DAWN methodology? The best answer I've heard to that question comes from Charlie Munger, my co-distinguished alumnus. He says, try to be consistently not stupid. No matter how many brilliant things you do, it can all come crashing down due to one dumb mistake. Almost the entire reason that software has so many bugs and is so easy to hack is because of dumb or stupid things. For instance, C++ exceptions are probably the dumbest of dumb things. Fork is a dumb thing. Threads are dumb things, though processes are good things. Using Windows or Linux or any other software not originally developed for safety critical applications in a safety critical system, is not just stupid, it's reckless. In the context of software upon which lives depend, the first three principles of agile software development are wrong. Number one, continuous delivery of valuable software to the customer. No, safety critical systems must have extensive testing before every delivery to customers. Welcome changing requirements in late development. No, late stage requirement changes were not considered in the original safety design, so they cannot be incorporated into the product without a full review of the safety design with the new requirements added. Number three, deliver working software every couple of weeks to a couple of months. No, that is not enough time to properly test software upon which millions of lives depend. Did I slay enough sacred cows yet? To accept the Dawn methodology, you have to slay about 100 more. That's the result of 46 years of experience and experimentation and study. Some people say that I'm just an old fogey who doesn't like any innovations in software development introduced since I learned to program 51 years ago. They claim Dawn's restrictions make it impossible for them to develop software with the capabilities and in the time frame required for success in the commercial market. You know, when they talk about success in the commercial market or commercial realities, what they really mean is making lots of money. So what they're actually saying is it's okay for them to do reckless things that put millions of lives at risk because that's the only way they know how to make lots of money. The Dawn methodology includes safe and secure alternatives for accomplishing everything that these dumb features do. We never have trouble finding a way within the Dawn methodology to implement any system with greater capability and performance than with normal commercial practices. And since we can quickly find every bug, we can get to market faster too. Applying the Dawn methodology in every safety critical industry, in 5 to 10 years, we can completely displace the current generation of unsafe, defective software that runs the world with new, robust, stable, reliable, safe and secure software that will prevent anyone from tampering with our infrastructure, our lives, our data, our privacy, our money, or our property. If I'm wrong, we're doomed. But we can do the impossible. Thank you for your consideration. I'm now open to questions.
Thank you, Dan. That was great. Insightful, provocative, as expected. We've already gotten a lot of questions during the presentation and also before as part of the registration. And so, but I do want to encourage everybody who still has questions to put them in the chat. We'll be filtering through them as we do this Q&A session with Dan. And if you'd like, you can include your affiliation with Caltech, your degree and your year, whether you're an alum, a student, associate, things like that with your questions. And I'll say them when I'm reading out the questions to Dan and chatting with Dan about them. So Dan, if you want to come back now and join me, we can start the Q&A session. And the first question I want to ask is one that was asked by a number of people, both before and during, which is the question of how these vulnerabilities that you've talked about really impact their lives. So how vulnerable are cars like Teslas or coming autonomous vehicles? How worried should we be? And even for more personal things like defibrillators, how hackable are they and what should we do about it in our lives locally?
There's a lot of questions.
Yeah.
So right now, it's very bad. The cars, we are now connecting all the cars to the internet. In fact, have been doing that for some years. People talk about self-driving cars. It's a little more obvious how serious that problem is, but actually your car is really self-driving right now. When you turn the steering wheel, you're not controlling any levers or pulleys or anything. It's just a computer input. Same thing for the brakes and the throttle. How do you know that? Well, your car stops when you're about to crash into something, even though you didn't hit the brakes. Right? That's a standard thing on most new cars. So clearly, you don't have to step on the brakes to stop the car. The software can do it itself. Same thing. cars have automatic steering, lane changing, all those features that are in most modern cars. It shows the computer's really in control. The only difference between what we're doing now and self-driving cars is that currently the software defers to you most of the time, as opposed to in a self-driving car where it doesn't defer to the driver very often or at all. So those cars have all these problems, and they are running terrible software that is easy to hack. It's been done numerous times. Researchers have shown, and these are small budget guys, if just a few people working on it, have shown how they can take control of the Tesla, BMWs, Chrysler cars some years ago. It keeps happening. So this is a really big problem already now because of the internet connectivity. They're easy to hack, and you can just take over the whole car. That's got to be fixed. Defibrillators are a lesser problem. If it's not actually connected to the internet, it's not all that big a problem. The problem with cars, I mentioned, what's the problem with cars? Yeah, you can hack a car. It says that sounds bad. You could drive somebody's car off the road. That's not the point. The point is that all the cars made by a manufacturer in a given model year are running the same software. That's millions of cars. If you can hack one of them with one bug, it's in all of them, so you can hack all of them. And you just completely conveniently place them all on the internet, so that now somebody can create a bot army and take control of 2 million cars and drive them all into oncoming traffic. That's the catastrophe that we are looking at today, that is feasible today.
Okay, so what do we do about it? What do we just buy old cars?
Well, the first one is, I've actually advocated this, and there's some people who've advocated it. The right answer is we need to disconnect those cars from the internet. If they weren't connected to the internet, then again, you could crash one car, maybe you could take over one car. That's bad, but we would survive. But if you just disconnected all the cars from the internet, then a hacker couldn't get to all of them. They could only get to the ones that they could see or get close to. A second and less troublesome approach, which I've advocated, all of these are just temporary band-aids, they're the wrong solution in the long run, was to put a switch in the car so that you could turn off your internet connectivity. Like if you're just driving somewhere, again, they can't take control of your car if it's not connected. So if you just have a switch on your dashboard that says turn off the internet, and then they couldn't take over your car, they could take other people's cars, but you could be safe. That we've advocated that to no effect with the government and the regulators. But the right answer is we simply have to write the software correctly from the start. The Silicon Valley mentality has completely dominated Detroit. They all want to be like Apple. They all want to be high-tech companies, and they used to do things more carefully. Now they just do it the same way that Apple does it. They just take software, they generate software. But Apple's got a cell phone, and if it crashes, you just reboot it. Your car crashes and you don't reboot everybody in the car. I'm not criticizing Apple for the way they do what they do. It is a totally appropriate solution for a phone. And same thing with Microsoft and other software like that. Makes perfect sense to use it in ordinary things. You just can't use it in a car. You've got to do it like we build airplanes. There is a complete methodology for writing software for airplanes that has worked amazingly well for 20 plus years. And it is really rigorous. And that's what we need for cars. We need people to follow that standard, or one at least as strong as that standard. Current car software standards are just bureaucracy, meaningless bureaucracy.
Okay, so that's a good segue into the other big theme of questions, which is, talking to Caltech audience. How do you actually do it? So can you tell us a little bit more about the fundamental design principles that underlie DOM?
Well, so as I said, there are a lot of things that people do wrong. That they are simply features which are prone to error. They're ones that I've seen again and again, other people around me make, that have taken a very long time to find and fix. The first thing you have to do is stop being stupid. Just stop doing things which are, I mean, I guess I'm insulting people, but because they didn't think about it. But if you think about it and we talk about it, I can show how these things are really bad. You have to start there. Mem copy, another thing that's, we don't disallow mem copies in our C programs, but you have to make it through a gauntlet to get your mem copy through the code. There are things you can only do that way, but you have to prove you didn't do something dumb, because that just creates so many bugs and problems in programming in C at least. But the other is that there is a methodology that is used in the aircraft industry for building software for airplanes. I saw somebody say this once, somebody familiar with Linux, and he was familiar with the aircraft standard. And he said, to meet the standards that we're talking about here, if we improved Linux processes, and security and safety things by tenfold, it wouldn't be enough. It's somewhere between 100 and 1,000-fold what you have to do versus what I mean is just common commercial practices. I mean, common commercial practices, any engineer can just kind of go into, any engineer at Microsoft can pretty much go into any program at Microsoft and change the code. And then there's one engineer is assigned to look at that fix and decide if it's correct. You can't do that with things people's lives depend on. You have to have a much more detailed process and review than that. So it's also thinking about how to do things simple. We have jokes around here. Well, here's my code, but if you'd given me longer, it would have been shorter. I mean, we literally say that. It's not better that it's longer, it's better that it's shorter and gets the job done. Just takes a complete attitude change. You can spend, again, the greatest compliment at Greenhills. People sometimes say this derisively. They say, what? You just wrote that program. I reviewed your program. You spent 6 months and it was what? A couple thousand lines of code. And it was so, it was just obvious how to do it. And I said, that is the greatest compliment you could give me. I spent 6 months, solved a problem that no one else had ever solved in some manner so good that basically some guy like you can read it and understand it and say it is really simple. Do you know how hard that is? That's really hard. That's the greatest compliment. You've done something really simple, straightforward, clean, and clear that gets the job done. And you can sort of look at it. And now you have a complete just documentation of everything it's supposed to do, testing, like it's hard to believe, like millions of lines of tests to make sure things happen. Constant testing. I'm not all against Agile, but the constant integration, that's great. Constant testing, that's great. We do all those things. But it is mostly about discipline and being very careful and thinking a different way. You're getting paid now, the programmers are getting paid nominally by the line of code they write, sometimes by the features that they can demo, but it's just the wrong methodology. You gotta change your point of view. Once you change your point of view, then you can actually start doing something about this.
So it seems like, Don is a mixture of cultural expectations, management processes, code development strategies, testing. Also, do you use things like formal methods? This was another question that came up a few times.
Yes. So on the operating system kernel, we did a certification with the NSA for security. This is what they wanted before they put us in the F-35 fighter jet, the most advanced fighter jet in the world. Their biggest concern is somebody will find a way to hack into their fighter jet and either be able to disable it or take control of it and turn it back against us. So they have a standard, a very, very high security standard. EAL 6+ certification level for the common criteria. And we went through and did that complete certification to that. Well, and no one else had ever even tried. No one else has done it. This involved a formal methods proof of security, and in particular, the concept of separation. Very important in security. Separation means that if you have two programs running on the same computer, they are separate if nothing that either one of them does can be detected by the other one. And that way we can run multiple different things on the same computer at the same time, as if they were running on different computers. So we did a formal proof of that separation in the kernel. This is very laborious. It took like, I don't know, 10 PhDs, some substantial period of time to do it. We actually have a program right now, which we're working on, which is to make that easier, to try to bring formal methods and proof into something. Right now, you have to be a mathematician to do proofs, in programming. I want it to be possible for programmers to do the proofs. It's an unachieved goal, but that would make it much more accessible and much easier. We've only done that on the operating system. On the other software, we rely on that baseline, but we don't do formal methods on the rest. We'd like to do more, especially for really important systems.
And so when it's not formal method guarantees, how do you make a guarantee like unhackable? What does that mean empirically? I assume there's metrics, and this was a couple of questions around what metrics are you using when you're studying these systems and trying to provide these guarantees?
There are many different guarantees that are done different ways. There are reliability guarantees, which testing can do. You can't prove security by testing. The reliability and security sound very similar, but they're different in that what reliability means is the thing does what it's supposed to do all the time. Security means it never does the things it's not supposed to do. Those are not opposites. And so security is almost impossible to prove by testing, because you can say, well, I tested it. Yeah, but if you just didn't test the one thing that you have that's an insecurity, then all the testing in the world won't find it. Stochastic testing can help, but again, it's not very good if the number of possibilities is immense. So the key is it has to come from the design. So for instance, one of the key basics, what I said is separation. If you can prove that your operating system can achieve separation, which is that I have two programs running at the same time, and nothing that one does can affect the other, then I can have security. I can run classified programs on my machine and unclassified programs on my machine and know that they can't interfere. The only thing I'm relying on is that the operating system does its job, which is the one thing we proved, and we proved that separation property. Most people try to do security from a very high level top-down thing. That's because they built their system. They didn't think about security on day one. Now, 10 years later or 5 years later, they say, oh, we should put some security in it. Well, it means passwords, things like that. In Unix and Linux, you have the root account. If you log into root, you own the machine. We don't have a root. We would never have any. Root is just terrible. Another of those horrible things. You just can't have anything like root in your system because it's a target for people to find one bug to gain control of the root. On the cell phone we built, there are 80 separate components, separate processes in that. If you try to break into that phone and you crack one of our systems, it's like you have a building full of rooms, and every room is locked and guarded. Most computer systems, again, terrible, what I call perimeter security. You build a military base and you put a fence around it. That's a good idea. What if somebody gets through the fence? Well, you have guards and locked doors and people checking badges and all these things, right? In a computer, if you get through the door, remember, you watch all these hacker movies all the time, and there's always a scene where the bad guy, or sometimes the good guy, is standing up. He doesn't know anything about computers, but there's a guy sitting at a terminal typing furiously, and they're saying there's a countdown of some sort. We have 30 seconds to get this done. It's the countdown. Somewhere around 2 or 1, they say, we're in, right? Every movie, it's always the same way. What does we're in mean? It means we've totally compromised the system. When you get past the one level of security in most computer systems, you're now a trusted entity. You can do anything. It's like the military base that says, if you get past the fence, you dig under the fence, you jump over the fence, you do something. Then as soon as you get inside, everybody says, oh, sure, and you walk up to the armory and say, I've got this shopping cart, fill it up with some missiles and grenades or something, and you can just walk out and no one will ever question you along the way. That's terrible security. But that's basically the security in essentially everything that we have. They all have some kind of root access, something that in which one compromise allows you to take over the system. You need it to be many difficult compromises to take over the system, and they have to do it one piece at a time. So that's how we use separation. We divide up all the responsibilities for all the different things separately. So even if you gain control of one, you have no control of any of the others until you find some way to crack that one. And that's really tough.
So that builds into the next thing. Again, there were lots of questions on this topic from like Tanish Nahata and Rajiv Gupta and others, which is, you've commented a couple times on, how it can take a long time to develop code in this, and, especially getting down to that short, simple to explain, simple to verify version of it. What is the trade-off between speed and this kind of software that never fails approach?
Speed
of development. Speed of development. Yeah, speed of development.
If you do it the right way, that is from the beginning, it's actually faster. When you write the software this way, you follow the rules, we can find every bug, and I mean every one, very quickly. We can find obscure bugs that happen once or twice in the field, uninstrumented systems. We can find those bugs. The whole process is completely different in terms of debugging. Essentially, debugging right now, debugging is an art. People who are good debuggers are master artists to look at a problem and be able to sort of divine the nature of what problem is and where to go to try to find it. It requires incredible skill and training. With our system, it's now engineering. Finding bugs is engineering. You sit down, you say, I know I'm going to find this one quickly. Even ones that are non-reproducible, problems that occur only in the field, those problems now, we can solve them. I mentioned it earlier, threads versus processes. We don't do threads. Threads are ununderstandable. They are the source of the most horrendous bugs, non-reproducible bugs. I'm not against multiple threads of control, but they should all be in their own process. Process in the Unix terminology, not threads, which are truly simultaneously operating things, which are sharing vast amounts of memory between them. You'll never find the bugs in that program. Anything complicated, you just can't do it. We go with a much better system that's easier to document, that's more deterministic, and in which you can log the information you need to find the bugs very quickly.
So you started that answer with, if you build it from the ground up. What if you don't?
You're doomed. I mean, if you're trying to make something that's secure or reliable, it's not going to happen.
So it's an all or nothing, basically. Start from the ground up. And
you can make bad things better or less bad, but they're still going. The talented hacker is still going to find a way through it. And we have to remember these hackers. We don't know exactly who these people are. We've been seeing these recent hacks, but this is now a military operation. Every major country has thousands and thousands of military to get into every system. What? Are you losing my audio?
You're back now. You drifted for just a second.
Oh, okay.
You're back now.
What was I saying? So the attackers we really need to worry about are not the ones we see every day. Those guys are more, juvenile delinquent kind of hackers. Not, that's the juvenile delinquents versus the professional thieves. The professional hackers are, they take these systems. We know, because who got hacked? The CIA got hacked. And you should just go read the list of programs they had. They could hack anything, every device. They literally had a list of every router, every system, every operating system, every phone and whatever. They literally had a gigantic library, and then they got hacked. The NSA did too. but just reading the list of the programs they had and what they would do, not even the source code itself, unbelievable. That's the CIA and the NSA, and the Chinese have it, the Russians have it, the Iranians are even pretty good at it, the North Koreans are getting good at it. It's out of control. We need things that they can't hack.
That leads into the next question, which came from a few people, but Balita Ong is the one that I'm looking at, which is, given all these vulnerabilities now, why have there not been more hacks to date? Why, do we just not hear about them, or is this something that should be increasing in the coming years, or will be increasing? That should be.
Well, so there are many more hacks than you see. Most companies try to cover it up. They only don't cover it up when they can't. Ordinarily, if they find a way to make somebody not know. Reading those 2 books I suggested, it's essentially the opinion of the people who know that every single company has been hacked, and they've gotten probably pretty much everything. I mean, all the technology, all the blueprints for basically everything. These are the military style hackers who are doing these things, and they almost always get away with it and don't get caught. You only hear about it when they get caught or when it's such a bad situation. But people say, well, how could that be that no one would do it? Think about this. For 40 years, anybody, not anybody, but anybody with reasonable resources could have taken 20 people and hijacked 4 airplanes and driven them into tall buildings. From 1960 to 2001, 40 years the technology existed and nobody did it. And it's not like no one ever suggested it. It was in several novels that people wrote about. There were even military people who talked about it, but everybody just dismissed it as, I don't know what. Why would anybody do that? Well, they want to hurt us. And of course, why would they do it? That's pretty easy. So, and it took 40 years for someone to take advantage of that opportunity to bring it down. Who wants to do it? I mean, we have the ransomware guys, they want to make millions of dollars, sure. But the Chinese government doesn't really want to attack us, I don't think. All right. I mean, that would, why? I don't think that's in their interest. I think the same thing for the Russians. They don't want an all-out war. Maybe the North Koreans are different, but I don't know. So to do the big thing, which is to take out the power grid. I mean, we didn't talk about that, but if they take out the power grid, this country's over. I mean, we can't live in 4 weeks, we'll be finished. There will be no food in the cities. There will be mass starvation, and there'll be no place to go. There'll be nothing. Some people will be able to get out. They'll be able to fly out. Some people have boats. They'll be able to make it to Mexico. They'll be jumping over Trump's wall to get into Mexico. They'll be getting on boats to go to Haiti. But I mean, that's just not going to be very many people. The rest are going to be, there's nowhere to go. There's nowhere to go. There's no food. There's nothing. And it'll turn into total chaos. It will be martial law. The military will survive. The military has food stockpiles. They've got gasoline stockpiles. They've got all sorts of stuff. We'll be living in a military operation. I mean, but they still can't get enough food. They can fill 3 million soldiers, but they can't feed 300 million people with their stockpiles. It's over. You just can't let that happen. And how do you do it? It's not ransomware. You find a way to blow up the transformers. Sorry, I don't know how to do that, but I'll bet somebody who's a great, engineer and understands these electrical systems can figure out how you could blow out the transformers by overpowering them. And you just rev up all the generators to red line and just let them keep going until they break apart. I mean, I don't know what happens, but I'm sure that after some point they just fall apart. You do that. How many manufacturers are there of those pieces of equipment? Not many. It can't be replaced in time. It's a catastrophe. We have to make this not happen. But here it is. We stand here right now with a problem. There are some band-aids we can do to solve the worst problems temporarily while we do the right solution to get it done right. And that's what we need to do. That's what I am proposing that we do. We sit down and we do it right.
So one other question, I mean, perfect to segue into this other theme of questions, which is how can people learn more about the tools and techniques in the DAWN methodology? It sounds like some of it is cultural and software development methodologies that could translate and that people could bring to bear in their own careers and their own avenues. Are there avenues where people can learn more about it?
At the moment, right. So at the moment, it's our internal culture. There is a significant amount of it written down. I give courses. I give courses on these methodologies. I've written documents and books on this. It's not in a publishable form, let's say, right? It's in an engineering format. I don't have time to make it pretty. I just have time to write it down and try to document these sorts of things. And it's in all sorts of different formats. I have a current program underway that is beginning, but not there yet, to try to do some of the higher level, less detailed things so people can sort of understand the concept of what we're trying to do, that will be published, or we will have materials that document many of these things and talk about many of these concepts in the next few months.
That seems like it could be potentially extremely impactful to spread these ideas and just best practices at that level.
And as you know, we are recruiting, right? I mean, that's what we do. We go to Caltech and we go to all the other major schools. We are recruiting and bringing people in to learn this stuff. We hire very few experienced people because there's so much they have to unlearn. And it's so hard for them to that's how I do it. You can't do it that way. You got to start people out the other way and say, no, not you have to stop doing what you're doing and doing. No, here's how you do this thing and here's how you do this thing. So we can build up from the bottom, not start at the top. So, 90+% of the people who work here came here out of college, and we've been showing them, training them how to do it, to build that methodology.
Okay, so I'm going to ask one last question that's a little bit out of the box, and I'll be very curious to hear your thoughts on this as well. But there have been a couple of people that asked around about the possibility of quantum computers and the impact they would have on security. Clearly, there's some impact on crypto, but security more broadly. And I was curious to hear your thoughts on that.
Well, I do not remember who it was, but it was a professor at Caltech. I was at a house here in Santa Barbara, in Montecito, I think, and was invited by a neighbor. And Kip Thorne was there, and there was somebody from Caltech, a professor who was doing quantum computing, and they gave little talks. And somebody asked a question, and they said, "Well, so when is it that this stuff is practical? That that we're going to actually be using this stuff in in real world systems?" And he said, "Maybe 20 years." My view is that's outside of my horizon. In 10 years, if it's 10 years, then we'll look at it, right? But the problems we have today are so vast, and there's no actual quantum computer that can actually break any of these systems today, at least I'm not aware of one, that we should focus on this problem. And in 10 years, if there's a new problem, and maybe quantum computing has the answer to the problem, right? I mean, you can look at it as an attack vehicle, but maybe there's a great defense vehicle there too.
That's a great point.
But I'm waiting until I see a real computer with a few megabytes of memory that can do stuff, and then I'll worry about it.
Good answer. Fair answer. So I think with that, we can wrap up the Q&A. And I want to thank you again, Dan, for taking the time and sharing your insights with us here. It was terrific. I enjoyed it a lot. And I can tell from the explosion of Q&A that the audience was really intrigued as well. So let me just say one more time, congratulations on being a recipient of the Distinguished Alumni Award. And I just wanted to give you one chance to say a final word if you'd like before we end the event.
Well, thanks a lot for the award and for the talk, and to have a chance to sort of put this out there. I have I have changed my focus from technology. We've really developed the technology that we need. Now I'm into getting people to understand it and getting it out there and getting people to deploy it in systems other than, the military government kind of systems that we've normally been in. This is for civilian use. That's my goal. My life goal right now is to find a way to get this done, because it really has to get done.
Perfect.
Thank you.
So with that, let me thank everybody for your attention and participation today, and have a great afternoon. Thank you.